Hello everybody, welcome back to the CCNA routing switching video series brought to you by ABY Design and Tech. You're joined here with your instructor Abdurrahim Chowdhury, and in this video we'll be having a look about the function of a router, the function that it performs in a computer network. Okay, so let's start off by talking about the main function of a router. What does a router do in a computer network which makes it so special? Well, simply put, a router allows communication between devices that reside in different networks. So going back to our previous video, we saw how a switch can be used to provide local communications. So it's similar to being trapped on an island and being isolated from the rest of the world. You can only talk with the friends on the same island that you're trapped on. So essentially that's what a switch does. Switch just allows for local communication. A router, on the other hand, allows us to communicate with the outside world. Now, a prime example of what a router can do, just look at your home router. So whether you have BT or Virgin provide your internet service, they will provide you with what is called a home hub. That home hub acts as a router. And what does that allow us to do? That allows us to connect to the internet. So following on from our island example, it's as if we built an airport on our island. So now that we've built an airport on our island, what can we do? We're not isolated from the rest of the world. We can now go and visit different countries across the world. Essentially, that's what a router allows you to do. A router allows you to get off your network and allows you to communicate with a device on another network. In this case, it could be the internet, or in most examples, it is going to be the internet. The devices on the network know that they can communicate outside of their network by using the router. So there's some settings that we configure on our devices, computers, laptops, etc., which tells them that if this device you want to communicate, if this device doesn't reside on your network, then you can use your router to communicate with those devices. Okay, so let's have a look at the router in action. So in this example, Bob needs to send an email to Brad. He's thinking, I need to send an email to Brad, but Brad is not on the same network as me. How do I reach him? And then Bob realizes, okay, I've been programmed to know that if I want to communicate with someone on another network, I need to go through the router on my network in order to reach Brad. So the next thing I'm going to do, I'm going to send this email all the way to my router, as my router will know how to reach Brad. I've been assured of this. The router receives this email from Brad, and he's like, Bob. He's like, okay, so Bob sent me this email. So the router doesn't actually know it's an email, it just knows it as a piece of data. So he said, okay, Bob sent me this piece of data. He wants to send this to Brad. Okay, now looking at my routing table, again, we'll go into the routing table a bit later on in this video, but I know that I can reach Brad as I'm connected to the same network that Brad's connected to. So I'm going to send this piece of data all the way over to Brad, no problem. Now Brad has received this piece of data from Bob. Okay, I can see this piece of data was sent from Bob. Let me open it, similar to how you would open a letter, and let me see the contents. So he opens this piece of data and realizes, okay, this is an email sent from Bob. I can display this on my computer and I can see what the contents of the email are. Okay, so in simple terms, that's how a router works. It just allows us to communicate from one network to another network. That's the main function of a router. Obviously, routers can do much more than that, but at a base level, that is the primary function of a router. Now let's dive a bit deeper. Now that we have seen how a router works, let's dive deeper into what is going on behind the scenes. Now, a router works at layer 3 of the OSI model. We'll talk more about OSI model, TCP/IP model in a later video. But just realize that with network communications, it's split up into layers. The reason why it's split up into layers is so it allows for flexibility. And so you can think of this model as defining a set of rules and guidelines that all computers must follow in order to be able to send and receive data on a computer network. Similar to how we have rules and guidelines on how we should drive on the road. Now, a router routes packets to different networks based on IP addresses. Again, you're probably thinking, okay, Abda, what's a packet? So This OSI model that we'll look at later, there's different stages to it. So essentially, we take that piece of data, and this is in simple terms. So obviously, a lot more is going on behind the scenes. But in essence, we take that piece of data, and as we move down the OSI model down to the different layers, we're adding more and more information onto that data. Now, if we're looking at the technical term for a packet is defined as a piece of data which has got IP information added to it. In the previous video, I talked about frames. So a technical term of a frame is a piece of data which has got not only IP information added to it, but also a MAC address information added to it. Now these essentially these terms are used interchangeably in the real world to define data that we're sending. So packets, frames, etc. Essentially all it is just a piece of data, but with more information added to it so it can get from point A to point B. Now, I know what the first questions on your mind is going to be. What's IP? So what's an IP address? So you could think of it like this. An IP address is a logical address and is used to group devices into a network. And this changes as we move around to different networks. Okay, so another question you guys probably have, what do you mean by logical IP address? So let's first have a look at what a MAC address is. So from the previous video, we know that a MAC address is what we call a physical address. In that no matter which network you move to, that address will all stay the same. Now the reason why IP is a logical address is because depending on what network you connect to will depend on what IP address is assigned to your device, what IP address is bound to your device. It changes as we move around. As an example, let's say you bring your laptop to your workplace, you connect to the Wi-Fi. You're going to be assigned an IP address. The IP address is bound to your device. And the IP address is unique for every device in the network. So as an example, your laptop is going to have a different IP address to the computer in your workplace. However, your MAC address stays the same. So your MAC address is a physical address which is on your device. However, if you were then to take your laptop home, you would lose the IP address that you were assigned in your workplace, and you would be assigned a new IP address as you move from your workplace over to your home network. So it's a logical IP address because it's only bound to your computer, to your device, as long as you're on that network. The reason why a MAC address is a physical IP is a physical address because no matter which network you connect to, that address is going to stay the same. So in an example, as you move your laptop to your home network, you obtain a new IP address. Now you're part of that network. Your MAC address stays the same, but your IP address changes. And that IP address that you were using in your workplace network, the IP address could be assigned to another device. So let's say a colleague brings in their laptop, the IP address could be assigned to their laptop. So the IP address only has significance whilst you're connected to that network. The MAC address always has significance all the time because it's the physical address. So what does this mean? This means that no matter who manufactured the device, so obviously we have different manufacturers of laptops, HP, Dell, Lenovo, etc. We can group devices together based on the IP address. And you can think of the IP address as being the same as a postcode. So a postcode applies to us when we live on a house on that street. So a postcode identifies a group of houses that are in the same area, so are in the same street. It's similar to with an IP address. It identifies a single device within that network. So again, grouping devices. So essentially it says that you can reach the devices with these IP addresses by going to this network. However, when we move to a new house on a different street, our postcode changes. Similar to if we move to another network. So let's say we pick up a laptop, we move to another network. So let's say now from home we go into Starbucks and we connect to their Wi-Fi. We're going to get a new IP address. Similar to if you move house to a different area, to a different street, your postcode is going to change. And if you think about it, all a postcode is a bunch of letters and numbers used to identify a group of houses. Similar to how an IP address is a bunch of numbers used to identify a group of devices, and also then used to identify a individual host. So it's important that with an IP address is split up into two parts. The first part of the IP address is known as the network part. This is used to identify that group of devices. So you could think of this as being the first three letters of your postcode. The first three letters of your postcode, they identify the area that you live in, your town, your area. So first it identifies the town or city that you live in, and then the specific district within that town or city. The next three letters / numbers of the postcode, they identify that street within that district. Similar, that with an IP address, the first part identifies the network that you belong to, and then the second part, known as the host part, identifies that specific device within that network. Again, we're going to see more of this later on in this video. Okay, so let's dive a bit deeper into what IP is. So an IP address is a 32-bit numeric number, which is written as 4 individual numbers separated by a period. Now, as each number in the IP address can be up to 8 bits in length, it can have a value of 1 through 255. So below is a prime example of what an IP address can look like. In this case, the IP address is 192.168.200.10. Now, the value in each of these parts of the IP address, so let's call them octets. So, example, 192 is the first octet, 168 is the second octet, 200 is the third octet, and 10 is the fourth octet. The reason why they call each part of the IP address an octet is purely because it's 8 bits in length. So, if you convert this into binary, it'll be 8 bits in length. So each of these octets can have a value between 1 through 255. So this is just an example. I just picked these numbers at random. It cannot have a value outside of 255. So as an example, you'll never see an IP address such as 256. It just isn't possible. So 256.1.1.1, that's not valid IP address because the first octet or the first part of the IP address is not within the 1 through 255 range. So let's dive a bit deeper and talk about more IP. So IP versus MAC, what's the difference? So IP is a unique address on a network. MAC is a unique address for our device. So again, IP, it's only important for when we are connected to the network. So as an example, if I go to Starbucks, I connect to their Wi-Fi. The IP address I'm assigned only has significance while I'm on that network. So people can identify, okay, this laptop, let's say Abder's laptop, is part of the Costa network. And this is its IP address. This is how I can identify this device. If I was to, let's say, go to another restaurant on the same day, let's say Nando's, I connect to their Wi-Fi, they'll be like, okay, now Abder's part of the Nando's network, and this is Abder's IP address. So IP allows for great flexibility because we can move between networks seamlessly without causing any issues, because essentially all we're doing is that as we move between different networks, we're just joining a different group, and then we're being identified with a unique IP address to specifically identify us within this group. Now MAC is a bit different, as MAC is a unique address. So each device has a unique MAC address, and this doesn't change as we move between networks. So my MAC address is going to stay the same whether I'm in Costa's network or Nando's network. It's always going to be the same. It is carried with us and stays the same. Now we communicate using IP addresses. Now, I know what you're thinking. You're thinking, well, Abder, in the previous video, you told me that we communicate via MAC addresses. This doesn't make any sense. Well, let's break this down, okay? So protocols use IP to communicate, as it allows communication no matter if you're speaking with someone on the same network as you, or you're speaking to someone on a different network. So, breaking this down more further, protocols such as HTTP, that allows you to essentially view websites. Protocols such as TFTP allow you to transfer files. Protocols such as SMTP allow you to send and receive email. These protocols work using IP. The reason being is because it allows for great flexibility. No matter whether you're communicating with a device on the same network as you, or you're communicating with a device on a different network, those protocols will work. It would be an absolute headache if we had to design protocols to use both MAC and IP. So as an example, let's say that we designed a web browser which only allowed for you to connect to a device on another network or a web server on another network by using IP, and then they created a separate web browser which only allows for local communication. And that would be a headache because we'd have to have both applications installed on our computer, and that means that every application or every protocol that we use to communicate in a network, we'd have to design both the IP and a Mac version. This way, by only using IP for communication, it allows for simplicity in that we can essentially have one application to rule them all, one application to both communicate using devices on the same network and to communicate devices on another network. Again, Mac only allows for local communication, and we'll see why it only allows for local communication a bit later on as well. Okay, I know what you're thinking. Okay, so I understand IP addresses allow you to group devices together. Essentially, as you move between different networks, you're essentially joining a different group. And your IP address changes as you move between different networks. The MAC address stays the same. You may be thinking, okay, so what's the difference between IP and MAC? When would we use IP? When would we use MAC? And why do we need both IP and MAC? Think of it like this. IP, that is where we need to get to end to end. That's the final destination where we're going to. MAC, this is where we need to get to our final destination. So this is where we go to next to reach that final destination. And this changes from each network's perspective. So let's use an analogy. Let's relate this to using a GPS. If we think about it, when we type in a destination address on our GPS will calculate our current location, it'll calculate where we're going to, and it will guide us on which direction we must travel. However, which direction we go, where we need to go to next, changes based on what street we're on. So let's have a look at an example of this. So as an example, let's say that we live somewhere around here in Crown Heights. Type in our GPS Washington Square Park. So where we're coming from is Crown Heights, where we're going to is Washington Square Park. That's never going to change. So the final destination is always going to be Washington Square Park. However, the GPS will say, well, you can't just go to Washington Square Park directly. You have to go down certain roads in order to reach that destination. So I'll say, okay, let's go north on Crown Heights, take a left, let's go down, let's say 3rd Avenue, etc., Atlantic Avenue, we go over the bridge here, we go through Lower Manhattan, and then we reach Washington Square Park. So as we go down each street, as we go down each road, the next road or the next street that we need to go down will change depending on our location or essentially where we are in our route to reach Washington Square Park. And this is very similar to how IP and MAC address works with a network. So the IP address will define, okay, this is where I want to get to end to end. This is going to be my final destination that I want to get to. The MAC address, on the other hand, defines where we need to go to from each network's perspective. So essentially, it's as if as this data is moving between networks, it's where do I go to next in order to reach this final destination. Similar to, in this analogy, how where we're coming from and where we're going to never changes. So we're coming from Crown Heights, we're going to Washington Square Park. However, the streets we have to take, the roads we have to take are going to change as we get closer and closer to that final destination. So why do we need MAC then? So like I said before, the question you're asking yourself is, why do we need to use MAC address when we communicate using IP address? And the analogy I'm going to use for this one is, let's think of a car with an engine but without wheels. So the engine, that's what gives the car the power to move forward. However, the car can't go anywhere if it doesn't have any wheels. You may think that's simple, but in a similar fashion, or that's common sense, in a similar fashion, IP allows us to communicate whether we are on the same network or separate networks. But the data will not move anywhere if we don't use a MAC address to move it. So with this analogy, even though the engine is what gives the car its power to move forward, to go from point A to point B, the car can't travel from point A to point B if there's no wheels on the car. The car is just going to stay essentially standing still. It's not going to be able to move. So you're probably still confused. So let me break this down even further. So IP is layer 3, MAC is layer 2. So again, we're going to get into the layers of communication later on, but just realize this. Network communication, it was designed in layers for flexibility. So layer 2 protocols focus on moving traffic from one point to the next. So like I said, is that as this data we're sending travels between different networks, the MAC address is going to say, okay, now that I'm in this network, who do I need to send this traffic or this data to next to ensure it gets to its final destination? Layer 3 protocols, they focus on grouping devices together and defining where that data needs to travel to end to end. So, Layer 3 protocols are group devices together to make them more easily reachable. Like I said, it's easy to identify devices by the group they're in. This allows for flexibility because essentially as we move between different networks, we can join different groups, and again it makes everything reachable because that group exists before we've even joined that group. And like I said, IP focuses on defining where the data needs to go to and from end to end. So you can see from these explanations how IP relies on MAC. So IP addresses rely on MAC addresses, purely being because IP defines, okay, this is where we need to go to, point A to point B. However, like with the analogy with a car, if the engine doesn't have any wheels, or the car has an engine but then doesn't have any wheels, it's not going to go anywhere. Similar with layer 3 protocols, in this example IP, we can give that data an IP address, a source and destination IP address, so where it's coming from, where it's going to. But if we don't use the MAC address to move it from point A to point B within the same network, the traffic's not going to go anywhere. Essentially, the MAC address defines, okay, this data is now in this network, where do I need to go to next to reach this final destination? Again, similar to how the analogy with the GPS, how even though the source and final location are going to stay the same, the streets we need to go down to reach that location are always going to change. Now what does that mean? This provides flexibility as it means that we can change the layer 3 and layer 2 protocols independently of each other. So let's look at an example of this. So in this case, we've got a typical network, and so just to make things clearer, this represents its own network, this represents its own network, and this represents its own network. Essentially, a router has got physical interfaces which we plug into. Each interface represents a different network. Now, all these devices in this network, so Bob's got an IP address, so there's Brad, so there's this router here and this router here. Even the switches themselves, there will be assigned IP addresses for management purposes, so we can connect to them remotely and configure those devices. So in this case, we can see the Ethernet is one type of layer 2 protocol which uses MAC address. HDLC is another type of layer 2 protocol. Now you may be thinking, how many layer 2 protocols are there? And the answer is there are quite a few layer 2 protocols, but the beauty of having network communications defined in layers is that we can use different protocols at each layer without affecting the other layers. Okay, so again, that's probably confused even more, but so in this example, Bob and Brad, they want to communicate with each other. Okay, Bob's got an IP address, so does Brad. Obviously, Bob realizes, which we'll speak about in a little while, that Brad resides in a different network to Bob. Okay, so now Bob will send an email to Brad. It's going to build this data. So it's going to put this email into let's say a piece of data that it wants to send to Brad, and it's going to essentially define, okay, this is the IP address this data is coming from, this is the IP address the data is going to. It's also going to define the MAC address. So in this case, the MAC addresses are going to be, okay, so Bob's going to think, I need to get this data all the way over to Brad. Okay, I know that I can't send this data directly to Brad because he resides in a different network. Obviously, I need to follow some path or some route to get this data to Brad. So essentially, this is like going down the different streets with the GPS example, is that we just don't go straight from Crown Park to, let's say, Washington Park directly. We have to go, we need to follow a route of streets in order to reach there. So Bob's thinking, okay, so in order to get this data to Brad, who do I need to send this data to next? So in this case, it's going to say, okay, I can send this data all the way to my router up here because I've been told that he would know how to reach Brad. So this data travels all the way to this router up here. Now, this router, when it receives this piece of data, it receives this piece of data via this interface here. It's going to look in its routing table, again, more about that a bit later, and when it's, okay, I know that to reach Brad, I need to send this data all the way to this router over here. Now, this is where the beauty of having different layers for communication come into play. Now, the link connecting this router up here to the router on the right down here is a what we call a point-to-point link. Again, more about point-to-point links later on. But just realize that point-to-point links, they essentially do what it says on the tin. They allow for one device to connect to another device, so point-to-point connections. Point-to-point links, they do not use Ethernet to communicate. They use HDLC. So now, would you think, okay, is that going to cause a problem when the router at the top tries to send this data all the way to the router on the right? No, it won't. The reason being is because the only thing that has to change is going to be the layer 2 information. So in this case, instead of using MAC addresses to send this over to this device down here, the router is going to use some another sort of layer 2 addressing, another sort of layer 2 information to get this data from up here all the way down there. Nothing else of the data, so none of the IP addresses or anything like that have to change. So what I'm saying is that by splitting our network communication into layers, we can change a layer 3 protocol without having to change all the layer 2 protocols beneath it. We can change a layer 2 protocol without having to change the layer 3 information. Everything's interchangeable, everything's flexible, and obviously eventually this data is going to end all the way up at Brad, and Brad can view that email. So let's dive a little bit more into IP. For each computer on our network, we need to configure our IP settings. So there are 3 main IP settings that we configure. The IP address, which is the unique ID for your device. The subnet mask is used with the IP address to identify your network ID, and the default router, your gateway out of this network. So in this case, the default router is going to be the router on your network, and you can use that router to reach networks outside of your network. Now, subnet mask basics. Okay, so probably the subnet mask is a very, very important piece of IP information, as the subnet mask is used by the device to identify whether the device they wants to communicate with resides on the same network as itself or resides on a different network. So your subnet mask is used to break down your IP address into 2 parts, a network part and a host part. So think of it like this. The network part identifies the network this computer belongs to, and the host part identifies your computer within this network. So why is this important? All computers in the same network need to have the same value in the network part of their address. So think of the network part as the group that you want to join. Essentially, to be able to join this group, let's say that you want to join this group called the green group, and everybody can identify that you're part of this green group as you have to wear a green t-shirt. So that's going to be the network part. The network part identifies, okay, this computer belongs to this network. Similar as if you join the green group, you're going to have to wear a green t-shirt. However, the host part is used to identify the computer within this network. So in a similar fashion, even though you've joined this green group, you're still going to have something unique about you to identify yourself within this group. So subnet mask magic. So let's have a look at some examples of the subnet mask. Okay, so let's say we have IP 192.168.200.1 and subnet mask 255.0.0.0. Okay, so this 255. So let's just take a basic view of it. Whenever you see a 255 in a subnet mask, that means that octet or that decimal number equals the network address. So in this case, we have 1, 2, 3, 4 different decimal numbers, and we have a 255 in the first decimal number. So that means that the first number in the IP address represents the network address. So that means that in this case, 192.168.200.1 is part of the 192 network. 192.169.100.5, that's also part of the same network. In this example, we have 192.168.200.1. Now, if the subnet mask is 255.255.0.0, as we see 255 in the first 2 decimal places, that means that the first 2 decimal numbers of the IP address represent the network address. In this case, we have 255.255.255.0. The first 3 decimal numbers of the IP address represent the network address. Now, why is this important? It's important as depending on the subnet mask dictates how many so essentially it dictates what decimal numbers have to be the same for devices in that network. So now what that means that Any device which joins this 192 network, the IP address has to begin with 192. And then the next three numbers can be used to uniquely identify that device. If a device were to join this network, the 192.168 network, it means that their IP address has to consist of 192.168, and then the last two decimal numbers represent that device within that network. So you can think of it as a unique ID for that device. And the same in this case. If a device were to join this network, the 192.168.200, that means that their IP address has to start with these three decimal numbers, 192.168.200. Then this last number can be used to uniquely identify that host within that network. So in basic terms, so SUBNET mask says, okay, if you want to join this network, your IP address has to start with these numbers. So anywhere there's a 255, that number has to be the same for all devices in the network. So like I said in this example, the first we have 255, 255, 255. That means that for any device within this network, its IP address always starts with 192.168.200. Now, wherever you see a 0 in the SUBNET mask, to be fair, it gets a lot more complicated than this, but at the base level, this is the easiest way to kind of grasp how the SUBNET mask works. Whenever you see a 0 in the SUBNET mask, that means that the corresponding decimal number in the IP address can be any number and is used to uniquely identify that device. So in this case, if you go to the second example over here, these last two numbers, they can be any value, and they're used to uniquely identify your computer or your laptop with the network. But when you connect to this network, your IP address has to begin with these first two decimal numbers. So the importance of the network ID. Now you're probably thinking again, why is the network ID so important? Now the network ID is used as a group address. It's just like your postcode. Essentially, the network ID says, hey, if you want to reach anybody in this group, then just come over here. And the network ID is used by routers when they route packets from one network to another. Now, it's important to understand the difference between routing and switching. So switches, they switch packets. So switch packets or switch data, all that means is that we're receiving data on one port and we're sending that data out another port. However, that data is staying within the same network. Routing is where a router takes data it receives from one port, sends the data out another port. The reason why it's called routing is because that data is moving from one network to another. So routing is when data moves from one network to another. Switching is where data moves from one port to another but stays within the same network. Now, why use IP and on Mac? Now, another question you may be asking yourselves is, why do we use IP for routing and on Mac? Now, we use IP for routing as we can use a group address like the network ID to represent all the devices on that network. And if we use MAC addresses, then we need an entry for each MAC address. Now, this is not a good idea as we have billions of devices connected to the internet. Okay, so you may be thinking, okay, so how does using the network ID, how does using this group address help us? So routers, they know where to route packets next by using what's called a routing table. So you can think of a routing table as being the same as a MAC address table. So the MAC address table says to reach this individual device, send the data out this port. The routing table says that to reach all devices in this network, send this data out this port. So this is why IP is used for routing. So essentially, we could have a route in the routing table that says, okay, let's say in this network down here we have 200 devices. Does that mean that in our routing table we need to have 200 routes, saying that to reach all these devices in this network, 200 routes, we essentially just use the same path because those devices all together, they're all in the same group, but let's list them individually and say, oh, okay, to reach all the devices you can use the same path. No. The routing table actually says that to reach all devices which are in this network, you can use this single route. Now we've got billions and billions of computing devices which connect to the internet. Can you imagine the headache it will cause if we had to use MAC addresses? So with MAC addresses, we can't do this logical grouping as MAC addresses are independent and there's no way that we can group MAC addresses. So MAC addresses are widely different from computer to computer. And again, each manufacturer essentially manufactures its device with a different type of MAC address, and there's no way to essentially use one MAC address to represent all the devices on a network. However, with IP addressing, you can use what's called a network ID, which is think of this as the group address, and this group address represents all the devices on that network. And this makes our routing table smaller and makes routing more efficient. So, as you can see from these slides, IP is the winner when it comes to routing. IP allows flexibility. Again, we can move between networks without an issue, as IP addresses are only bound to a device whilst it is connected to that network. And no information needs to change on the router as we move around to different networks, as the router will have a route to the network ID. So the reason why IP allows for such great flexibility is that as you move around between different networks, those networks don't cease and then exist when we move around. Those networks are always in existence. So that means that this table that these routers have on how to reach these different networks is always going to stay stable. So we can move from, let's say, Costa's network to Starbucks network. Nothing needs to change on the routers, and will always be reachable because that network has always existed in the first place. However, let's say that we were to use MAC addresses. A MAC address does not change as we move around. And if we were to use MAC addresses to actually route traffic between different networks, it's going to cause massive issues. And that means that as our device moves to a different location or to a different network, the routing table is always going to have to change. Again, causing instability in the routing table and causing issues. And you have to remember, these routing tables, they're stored in memory. Like the MAC address table, they're stored in memory. If that memory is of a finite size, a finite amount. Think of this memory as like your hard drive on your computer. Your computer may have a 1 terabyte hard drive, a 5 gigabyte hard drive. It doesn't have an unlimited amount of storage. There's only a limited amount of space. The same thing with memory on a router. The memory on a router is only a finite amount of space. So the routing table can only be a certain size. If the routing table then starts to exceed that size, first of all, we can't put any new entries into the routing table, or if we do put new entries into the routing table, it's going to overwrite older entries, and it's going to cause all sorts of issues, as there won't be full reachability as needed. And this is why we only use MAC addresses for local communication and not global communication. Okay, so I've been talking all about this routing table. Let's dive into what the routing table is. Now that we understand IP, how does the router know how to reach a network? A router will build a routing table which is similar in concept to a MAC address table. The routing table will list each network the router knows how to reach and a route to that network. The routing table is stored in memory, so like I said before, a large routing table is not desirable. So this example shows what the routing table looks like. So on the actual routers themselves, this isn't what the routing table looks like. It's not actually going to be a table and list information in this sort of manner. However, the information it does list about each route is going to be similar. And so the routing table essentially says, okay, this is how I reach this network. So in this case, we have the 200.110/24 network. Now, you're thinking, okay, what does this /24 stand for? So this /24 is used to represent the subnet mask. In the subnet masks that I showed previously, the one thing that they all have in common is that they're all, if you were to convert the subnet mask into binary, they're all a bunch of binary ones followed by a bunch of binary zeros. Now the /24 or the /16 or the /8, they identify how many binary bits or ones in that subnet mask. As an example, a /24 is equal to 255.255.250. That's the subnet mask that is supposed to represent. /16 is supposed to identify a subnet mask with 16 binary ones, or a subnet mask of 255.255.000. A /8 identifies a subnet mask of 255.000. So the subnet mask is, again, this is a very important component, or very important part of the subnet mask. The subnet mask is essentially just a bunch of binary ones followed by a bunch of binary zeros. So a subnet mask can only have certain values in each octet. Again, we're going to expand on this as we start to dive deeper into IP, but just realize that this is what the routing table looks like. So the routing table shows how to reach that entire network group. Instead of listing how to reach each individual device within that group, it says that you can reach this group from here. And then as that data then travels into that network, into that group, then it's the switches which tell you, okay, now that you're in this group, this is how you can reach this specific device within this group. So again, we can see where IP can be used and where MAC address can be used. IP, again, I know I keep repeating this, but it's very important that we understand this. IP is used to group devices together and say, okay, we can have one route to reach this group. Now that we've finally reached this group, let's use the MAC address to identify how we can reach this specific device within this group. It's routing table confusion. You may be thinking, why does the routing table show the same outgoing interface for nearly all the routes? So if you go back to here, as you can see, the outgoing interface is essentially nearly the same for every single route. The routing table shows the path to take from that router's perspective to reach a given network. It tells the router what local interface it needs to use to reach that network. So a router has only got a finite amount of interfaces. Essentially, the routing table says, okay, to reach this network, I have to go out this interface. To reach that network, I need to go out that interface. Similar to if we were to use a GPS to travel somewhere, we can use the same stretch of roads or the same combination of roads to reach various different locations. The reason being is because from our local perspective, in order to reach those destinations, we are going to be using the same sort of roads. It's similar that with the routing table, it lists similar outgoing interfaces because it says, okay, I am the router, and from my perspective, I have to leave via this interface, or I have to leave via that interface to reach this network. So the interfaces are always going to be very, very similar. And interface equals port. So again, what I'll do is that once we've discussed all the devices that build in a network, I'll actually show you physically what they look like, because at the moment these symbols I've been showing you, like square for switch or circle for router, a router isn't actually a circular device. It's a square device or a rectangular device. The reason why I've been showing you these symbols is because in network diagrams you use certain symbols to identify certain devices. Okay, let's bring this all full circle. Okay, now we're going to go back to the example which is Bob and Brad and showing that they want to communicate. So before we talk about anything, let's talk about how this network is laid out. So we got the router up here. This router has a direct connection to the 192.168.200 network. As you can see, subnet mask 255.25255. So again, if you convert 255 into binary, it's just 8 bits of consecutive ones. So we've got 8, 16, 24. 24 bits of ones. And here we have, on the right, it connects to network 192.168.210.0. So that's the network that it connects to. Now, you may be thinking, okay, so in the 192.168.200 network, the router has the IP address 192.168.200.1. And in the interface, which connects to the 192.168.210 network, it has the IP address 192.168.210.100. So as you can see, it connects to these networks. And as you can see, that because the first 3 decimal numbers represent the network, it means that any device in this network, its IP address has to begin with his first 3 decimal numbers. So in this case, Brad, his IP address is 192.168.210, the same as, so those first 3 numbers are the same as the routers. However, if the last number was used to identify Brad was in that network, and if we had another host here, then his IP address would be 192.168.210, followed by another unique number. Okay, so you may be thinking, you said that each device has a unique MAC address, but why does this router have 2 MAC addresses? So, when we say the device has a MAC address, in reality, we're talking about the network card. So, a router, because it connects to different networks, essentially got different network cards built into the device. Because it's got different network cards built into the device, each port on the router has to connect to a separate network. We can't have 2 ports on the router which connect to the same network. So in this case, we can't have GI01 and GI02 both connecting to the 192.168.210 network. That breaks the rules of routing. Routers, each port represents a different network. So essentially, because a router has got multiple network cards inside of its hardware, each network card has its own MAC address. It's similar. So on our computers, you probably have a Ethernet port which you can plug into, and you probably have a wireless card so you can connect to the Wi-Fi. So you'll see this on computers, you'll see this on laptops. Your wireless network card will have a different MAC address than your wired or your Ethernet network card. So the MAC address is a physical address burned onto the network card itself. It's not burned onto the device. Hence, if we have multiple network cards, each network card would have a different MAC address and a different, essentially, physical address to identify the network card within our network. So in this case, going back to the example, Bob has an email to send to Brad. Bob thinking, let me compare my subnet mask to my IP to see which network Brad resides on. Okay, so he says, okay, so I know that Brad has the IP address 192.168.210.15. I have the IP address 192.168.200.10. And from my subnet mask of 255.255.255, I know that for Brad to be on the same network as me, his IP address needs to have, so the first 3 digits of IP address have to match. So let me go through this, okay? So 192, Brad has 192. Okay, so the first decimal number matches. I have 168, Brad has 168. The second decimal number matches. So far it's looking positive. I have 200, Brad has 210. That's where it stops. It's like, uh-oh. Brad is obviously in a different network to me. My subnet mask tells me that the first 3 decimal numbers have to match for us to be on the same network. However, I have 200 in the third decimal number. Brad has a 210. So Brad resides on a different network to me. So since Brad resides on a different network to me, I need to send this email to my default router, because my default router will know how to reach Brad. So as you can see here, the IP setting default gateway. The default gateway essentially says that if you need to communicate with somebody who's on a different network to you, send this data to your default gateway, as chances are he will have a route and know how to reach that network. Okay, so if any of you eagle-eyed viewers out there, you'll probably notice that the IP address has now changed from 200.15 to 210.15. I realized obviously that this example wouldn't really be any useful if the IP address was wrong. So I paused the video, I changed the IP address, then let's get back to the example. Okay, so Bob knows, okay, to reach Brad, I need to send this email to my default router. So he takes this data, he defines where this data is going to end to end. So he says the final destination of this data is going to be 192.168.210.15. So eventually I want this data to end up on Brad's computer. However, Bob has to think, okay, I know that I want to send this data to Brad. I know that I have to go through my default router. But how do I reach my default router? So how do I get this data from my computer to my default router? It does this by using the MAC address. So in this case, it's going to set the source MAC address as itself, the destination MAC address as the router. This way, when this data is received by the switch knows, okay, this data needs to be sent to this router up here. So I'm going to forward this out of my GI05 interface to this router. And so that's exactly what it does. So now this email has ended up at this router. So the router, once it's received this email, he says, okay, I received some piece of data from Bob. It has my MAC address, so it must be for me. So what does the router do? The router essentially strips off the MAC address. And he's like, okay, after looking at this email further, I have seen that I've been inspecting this data a bit more. And I can see that this data isn't actually for me. This data is for 192.168.210.15. So I can see that Bob wants to use me, wants to go through me to reach Brad. So let me check my routing table. Okay, so my routing table says that I can reach this network, the 192.168.210.0.24 network, by going through my interface GI 0/2. And he says, okay, now this isn't an exact route for Brad. However, Brad has the IP address 192.168.210.15. Since Brad has the IP address, he must reside on this network, because essentially this route is saying to reach any device with the IP address 192.168.210, you can use this route. Brad has the IP address 192.168.210.15, so he must be part of this 192.168.210 group. I found a route to get to the 192.168.210/0/24 network. This is the most accurate route I have, so I will now use it to send this data over to Bob. So, before the router sends this data, he doesn't change the IP address, because obviously the final destination we're going to doesn't change. However, he changes the MAC address, and so the reason why he changes the MAC address is because, like with the GPS example, as we travel from point A to point B, the streets we're going to be traveling down are going to change. In a similar fashion, where this data is coming from and where this data is going to on this local network is going to change. So it's essentially what the router tells us, the switch, is that this data I'm sending, this data came from my address on this network, and it needs to go to Bob's address, or sorry, Brad's address on this network. And so what happens is the router changes the source MAC address to the MAC address of GI 0/2, since this data is traveling out of this interface. So when a router sets the MAC address to use when sending data, the router is going to use the interface it's going to send this data out of as the MAC address. So in this case, the outgoing interface is GI 0/2, is going to set the MAC address to CCC. In this case, the destination MAC address is now going to change to Brad, because the router realizes, okay, I am directly connected to the same network that Brad connects to. I can reach Brad directly. So now I'm going to change the MAC address to DDDD. And to be fair, that's all there is to it. So this traffic, this data finally reaches Brad. Brad is able to view the contents of the email, and that's it. So we reached the end of this video, and let's just recap, just so I make sure that everything sinks in. It's essentially IP addressing, or IP, is used to logically group devices together into a network. Essentially, we have the network ID, which is used to represent the group of devices. Now, the reason why we use IP is for flexibility. So as we move from one network to another, we move from one group to another, we can get a different IP address as we move between networks, but by using IP, it allows us flexibility, as the IP address is only bound to our device, it only has significance whilst we're connected to that network. The MAC address is our physical address of our network card, which never changes as we move. Again, the IP address is similar to a postcode. MAC address is similar to a social security number or a national insurance number, in that no matter if we move house or not, that never changes. However, if we do move house and we move to another street, our postcode changes. We've seen where IP is used, where MAC is used, and we've seen why we need to use both. Again, IP just defines how we get from point A to point B end to end. The MAC address, or let's say these layer 2 protocols, so they define how we get there. So they define from each network's perspective, where do I need to go to next in order to reach that final location, the final destination. So as you can see, that wasn't, to be fair, I'd thoroughly recommend rewatching this video again so that it really sinks in about what IP is, what MAC is, and essentially how they both come together to allow us to send and receive data and to be able to communicate. Again, if you want to see more content like this, please subscribe to my channel. Please share this content. As I say every video, let's get world-class training to the masses. Thank you very much.